Okay, teachers, Wamoini and so on, we need to start. So, because otherwise we will not have time to do everything. If you want to do everything, you may not want to do everything. Um, Mafari, I hope you're there. I can only see the top of your heads. So if you could put your camera down a little bit. Um, oh, that's better. I can see people. There are humans at Mathari. Way! Hello, humans. That is good. Hello. Lovely, lovely humans. Thank you. Wamuini have gone off because they have eaten too much, so they have gone off to the hospital, it looks. Sharika have disappeared. Oh no, no, sorry, that's you, Fatma, isn't it? Kasumu, I don't know. Anyway, I'm recording it, so we will move on. We need to move on because otherwise I don't have time to do everything. I think we have to stop for your lunch at 1 o'clock. Is that right? I think it's 1 o'clock. So, does anybody know? Is it 1 o'clock? Cool, excellent. Okay, let's get on with it. Now, this seems like a very strange way of starting electrochemistry. If a lion could talk, would we be able to understand it? I put these slides into ordinary lessons sometimes. They are called thunks. They are difficult to answer questions, but they make people think in a different way. If you think about the question, it is very difficult. If a lion could talk, I mean, could talk English or Swahili or whatever, would we be able to understand it? Well, a lion's experience is very different from ours. Their thought about life is very different. Would we be able to understand it? Probably not, but we will. So it's just a question that gets your students to just think about something different. You'll come across another one later. Okay, so this is about electrochemistry 1, and in this one, I'm going to have to do fairly quickly. I hope it's good for you. We're going to look at redox first, oil rig and that sort of thing. We'll look at oxidation numbers. We'll look at reduction potentials or electrode potentials, and then voltaic cells. When you're doing electrochemistry, it is very tempting to put it all in the same box. You will have a problem doing this to your students, lighting up their bulbs with electrochemistry. Electrochemistry can be great, but it's quite difficult to make them enthusiastic about it unless you can do practicals. I just want to introduce an idea to you about learning, and that is that the best learners value their learning. Now, in my experience teaching your students, those of you I have, they do value your education. They are not always engaged with me. They do not take responsibility for their own learning enough. I think they are passive learners. And I want to try to make them improve their own learning based on the information they get back. In other words, to reflect on their own learning. And they have to make the decisions. Yestin Thomas, Mr. Yestin was talking about making decisions and choices and so on, and they need to do that. If we are chemistry teachers and we fill boards up with this sort of thing, what we sometimes do is confuse people. What we then sometimes do is stand in front of it and make it even worse. And what we are doing is making what we think is an interesting lesson or a detailed lesson too difficult for students to engage with. So we have to, one, make sure that we know what the students already know. We have to tell them what success will look like. We have to model. That means that I do, we do, you do. That means we show how to do it. We have to work ourselves to develop the way we ask questions. I don't know about you, but sometimes I ask a question and I say, If we start with 16 grams of methane, what I'd like you to do is to work out, oh no, hang on, wait a minute. If we, no, how much carbon, and that's a useless question. We need to develop good questioning. We have to plan for differentiation. That means finding easier material for those people who are finding it difficult and more complicated ones to challenge the better ones. We have to make sure that we do give proper feedback. And we have to make our links and connections to other parts of the syllabus really obvious. And we have to start all the students in the same place. That's what that lion was about. If they come into the lesson and they see something like that, they will always all be thinking the same thing at the same time and make them work harder than you. Okay, here we go. This is about teachers. These are nice quotes about teachers. I believe more than anything else, this one at the bottom from John Steinbeck. I want you to start to really think about your value in the world. I have come to believe that a great teacher is a great artist, and that there are as few as there are any other great artists. Teaching might even be the greatest of the arts, since the medium is the human mind and spirit. In other words, you as a teacher, you will be worrying, as this top one says, as Pico says. The fact that you worry about being a good teacher means you already are one. We do worry about being a good teacher. Try not to worry about it, just to get on and find ways of doing it. Okay, here we are. We're going to be going this way again. I do, we do, you do. I show them, we then do one a bit together, and then they do it. Lots of them doing it. Okay. I'm not going to do that. It's too quick. So this is electrochemistry. Electrochemistry includes redox in all sorts of bits, voltaic cells, and electrolysis. And you must try to keep the voltaic cells and the electrolysis separate because they will get them confused. Okay? So this is the sort of knowledge that they require before they get into electrochemistry. Very important. They need to be fairly confident about ionic bonding, properties, formulas. They've got to be able to write the formulas. They've got to know the redox, which is where we're starting. They've got to remember the reactivity series, and they've got to know a little bit about circuits. I start with a picture. My students all know what this is. This is Red Bull. And I say, no, it's not. It's red ox. It's a red ox. Okay, it's red ox. And when you write down all these different bits about what reduction and oxidation are about, and you say, there it is, you can say, learn that, or we can teach them it. And I believe we have to teach them it. So this is how we are. They will be confused if they are asked simply to learn it. It will not work if they just try to learn it. So let's go through it gently. This is what I do. Oh, I tend to use students with pens. So I will get 2 students at the front to remind them about ionic bonding. And I will have one person with 7 pens and one person with 1 pen. And one is called fluorine and the other one is called sodium. And it is obvious then, the one with the 7 needs one more and takes it from the first one. And takes it. The first one does not give it away. Sodium does not willingly lose electrons. That's not how it works. So here's an example. This is some magnesium burning. Very bright. That's in my laboratory. That's my finger down there, just about to do something. So what I do is I start with something that makes a lot of sense to them. Magnesium burning to make magnesium oxide. Obviously, the magnesium gains oxygen. So that's oxidation. For your more able students, you can say, but what is happening to the magnesium? I don't mean, is it gaining oxygen? I mean, what is happening to it? What happens to the magnesium atoms? And how about this? Here we have a reaction in which we have magnesium ribbon in dilute acid. Completely different reaction, or so it seems. Are they doing the same thing? Well, here's the magnesium reacting with hydrochloric acid to make magnesium chloride. We came across magnesium reacting with oxygen to form magnesium oxide. What is important is to try and get your students to discuss this. Is the magnesium doing the same thing or different? And what is happening to the magnesium? Oh, well, in both cases, the magnesium is losing electrons. So this is where the idea of oxidation definitions were widened, because it became obvious that gaining oxygen was oxidation, but gaining chlorine was also oxidation as far as the magnesium was concerned, because it was just losing electrons. Exactly the same thing is happening. So what we then do is we say, okay, let's remember that they are opposites, and then we can construct something that the students will understand. Okay, we've got oxidation is the gain of oxygen. Well, if that is true, then reduction must be the loss of oxygen. And if we were talking about electrons, and we said the magnesium loses electrons, then reduction must be the gain of electrons. We will have taught them about oxidation number. And from magnesium to magnesium 2+, it goes from 0 to +2. That is an increase in oxidation number. And nicely, reduction is a reduction in oxidation number. And you may want to put in the one about loss of hydrogen and gain of hydrogen. So develop the oxidation reduction definitions slowly. Start with something like this, move on to comparing it with something else, show that the magnesium is doing the same thing in each case, losing the electrons, then make them opposites. We know that, so yes, loss of electrons, gain of electrons, and so on. This is a thermite reaction. Oh, yes. The thermite reaction. In here we have aluminium powder and iron 3 oxide. And this is one that you can do if you have any access to chemicals. If you have some aluminium powder and some iron 3 oxide powder and a little fuse of magnesium, you can do this. It is an extremely good reaction that happens very quickly and shows the violence of redox. It is a very simple reaction, and at the end of it, the reaction is very quick. It produces molten iron. There's molten iron at the bottom. Okay, so you can use very exciting experiments to show people what redox can be like. Then we come across ways to remember it, and many of you will use oil rig. An oil rig is okay. Oil rig is oxidation is losing electrons, reduction is gaining electrons. That's okay. My one is slightly different. I use this guy. This is Leo, the lion, who goes grr. A bit of a stupid spelling of the noise that a lion makes, but that's because it stands for losing electrons is oxidation, gaining electrons is reduction. And actually, I think this is more natural than oil rig, because often in a question, they have to explain what is happening. And you go, losing electrons. Oh, it's oxidation. Gaining, something is gaining electrons. Oh, that's reduction. That's easy. So oil rig or Leo goes grr, no problem. And then we move on to oxidizing and reducing agents. And you have to start with something like a displacement reaction. In a displacement reaction, and it's good to demonstrate it, this is a very simple one to demonstrate. I do it with a beaker with some blue copper sulfate in, and I just add zinc. And it turns a pretty muddy sort of color to start with. And through the blue color, you cannot see that the zinc is turning red, but the blue fades very quickly because it's turning into zinc sulfate. And afterwards, you can see that the zinc is red because it has been coated with copper. Now, in this one, if we want to turn it into an ionic equation, all we have to do is to remember that in turning things into ionic equations, only the AQ split up. Whatever chemicals we have, only the AQ split up. So this will split into Cu2 plus and SO4 2-, and similarly the zinc into zinc ions and sulfate ions. We could get rid of the spectator ions, the sulfate ions. Then we get this. And then we can look at this with our students. This will take some practice for them to see what is happening. So you have to look at what is happening. The zinc, focus on what has happened to the zinc. The zinc has gone from zinc to zinc 2 plus. How? It must have lost electrons. Where have those electrons gone? They have gone to the copper. The copper ions have turned into copper. So you look at it like this. The zinc has turned into zinc ions. That must be losing electrons, which is oxidation. The copper ions have turned into copper. That must have been about gaining electrons. Gaining electrons is reduction. So that's redox, okay? And if you're using oxidation numbers, 0, +2, and +2 and 0, they are balanced. So that redox reaction cannot have more oxidation than reduction. So I teach them oxidation numbers. Now, I see from the Kenyan syllabus that oxidation numbers are mentioned in Form 1 and 2. To my mind, that is a funny place to do it because some people find it quite difficult. And so I do it a little bit later. I'm going to run through this. I'm going to miss that just for a minute. I'll tell you it in just a minute. So oxidation numbers. Oxidation numbers go like this. There are a set of rules. I only have 3 rules, and if the rules are obeyed, you can work out the oxidation numbers of almost anything. So here are the rules. You have to remember that rule 1 is most important, then rule 2, then rule 3. So if rule 3 would contravene rule 1, it can't happen. So rule 1 is very simple. Elements have an oxidation number of 0. Molecules have an overall oxidation of 0, and ions have their charge. So copper sulfate, 0. Aluminium, 0. Nitrate minus, -1. Cu2 plus, +2. Rule 2 is that under normal conditions in a compound, group 1 are +1 and group 2 are +2 and fluorine are -1, and they never change. Rule 3 is as long as rule 1 and rule 2 are obeyed, oxygen is -2, hydrogen is +1, and most elements have their valency. So nitrogen normally gains 3 electrons, so we would expect it to be -3 in a compound, normally. So rule 1 has to be the first rule that you obey. The second rule, as long as number 1 is obeyed, number 2 is okay. As long as number 2 is okay, number 3 is okay. So let's look at what we do. So it's the same as we did before, which is I do, we do, and then you do. In other words, the students do. So I show them one. I go, okay, let's do H3PO4. So I do it in a really simple way. I go like this. Oh, hang on. Let me just see. Rule 1 says that because that's a molecule, it's 0 overall. There are 3 hydrogens in this, and each hydrogen from rule 3 is +1, so it's +3. There are 4 oxygens, and they're -2 each, so that's -8. So therefore the phosphorus must be +5 because they must all add together. Now I normally actually construct it like this. I go, okay, I always put the one that I want to know last. So I go, I've got 3 hydrogens, I've got 4 oxygens, I've got 1 phosphorus, and I'm going to add it up. And at the bottom, I'm going to put 0 because it's a molecule. The 3 hydrogens will be +3. The 4 oxygens will be -8. And those 2 plus the phosphorus must be 0. So that must be +5. Okay, so simple stuff. Whoops. So I might do some more. So I often do KMNO4. I know I've given you the answers here, but that's the whole point of it, is to go KMNO4. Okay, I've got 1 K, I've got 4 oxygens, I've got 1 manganese. It's going to add up to 0. 1 potassium, that's +1. 4 oxygens, that's -8. Therefore, this is +7. Potassium manganate 7. But, and this is quite important, that there will be odd ones, and you need to show them the odd ones. So, for instance, let's look at K2O. Okay, I've got 1 oxygen, and I'm going to try. No, sorry, got it the wrong way around. My apologies. Hang on. So let's say I'm trying to find the oxidation number of the oxygen. Now, I think I know what it is. I think my rule says it's -2. So let's see whether that works. So I'm going to go, I've got 2 potassiums, I've got 1 oxygen, no charge to the whole thing, so it's 0. Rule 2 says potassium group 1 is +1 always, so that's +2. So the 1 oxygen must be -2. That's great. That works. But how about potassium superoxide? I'm going to ask about the oxidation number of the oxygen. Well, I've got 1 potassium, I've got 2 oxygens, the whole thing adds up to 0. I know from rule 2 that potassium is always +1, so it's +1. Oh, now normally oxygen is -2, but if it was -2, that would mean that the potassium can't be +1. And rule 2 says potassium is +1. Rule 3 says oxygen, no, it can't be. So the 2 oxygens must be -1. So each oxygen must be -1/2. Well, wow, that's weird, but it's true. That is what its oxidation number, its apparent oxidation number is. So show them the weird ones. So there's a set of them, and here are the answers. If you want to work them out, okay, you'll be getting this after the session. Now, then we're going to use oxidation and reduction. Fairly simple stuff. They probably know that the reaction of the halogens goes up the group. So the most powerful at gaining electrons, Leo goes G, gaining electrons is reduction. If I gain electrons from you, then you have lost electrons, so I am an oxidizing agent. So the best oxidation best oxidizing agent is fluorine. And then I introduce the electrode potentials like here, and I find that that is a large positive number compared with the other ones. And I just introduce it. I don't say anything about it. I just say, look, there we are. They're not going to understand what the numbers are, but they know the reactivity. Ask what happens in oxidation. point them to it. Okay? Talk about practical observations. Do some redox calculus. Here are some examples. Which ones are redox reactions? Can you find the oxidizing agent, the reducing agent, and so on? That's really important. Can they see what is happening here? Can they work out what is happening in oxidation and reduction? So carbon here loses hydrogens and gains oxygens. That must be an oxidation, etc. I've given the answers here. If you want to look at these, if you wanted to use any of these later, the answers are all on this sheet here. So in the first one is carbon, hydrogen, various answers down here, and it tells you why. Okay. Use examples like this one. Give them multiple choice because they can then go through them and spend some time trying to work out. Are any of these not a redox reaction? Have a look yourself. Are any of these not a redox reaction? Well, look, here's 1B. The magnesium is going from 0 to 2 plus. In other words, it must be losing electrons here. So that must be a redox reaction. Okay, that's just like the zinc and copper one. How about this one? In general, if an element becomes a compound, then it is redox. So which one is not a redox? I hope you're saying that one, because that is iron 2, oxygen -2, hydrogen +1, chlorine -1, iron +2, -1, +1, -2. Here's a teaching idea, quick one. We should try to make them active learners. And by that, I want them to talk about what they're thinking. If you have to explain things, not only do you get quite good at it, but you actually embed your memories a bit better. So you start a sentence, something like, you give somebody some words, and you say redox reactions are ones where, and they have to carry on the sentence. And then you stop them and you move on to the second person and the third person and so on. You can help them. You may be able to prompt them, but it's really good to get students to talk about their answers. Get ready to prompt because they'll stop talking. So you can then give another idea. Right. So we're on to electrochemical cells. Now, electrochemical cells, that's ones which actually produce electricity. And hopefully you will have a laboratory where you can show them something like this. But if not, show them pictures. Have something that you can project if at all possible, or at worst, draw on the board so you can talk about this is what it looks like. This is something where I do it at first. Okay. This is a copper in copper sulfate, zinc in zinc sulfate. Here the voltmeter is registering, I don't know if you can see that, but it says 1.08. Many of you will know it should be 1.10. Okay, so how do we do it? This is the electrochemical series, and it has all of the reactions written as reductions. That's why it's sometimes called the reduction series. They don't need to know how we find this number, the electrode potential. What they do have to recognize is that more positive things are more likely and negative things are less likely. You can take an example if you want, and you can say, would potassium be happier losing electrons, in other words, going from right to left, or gaining electrons going from left to right? And most of them know that potassium will tend to lose electrons. So going from left to right is a negative number. Going from right to left would be a large positive number. Talk to them about it. What does a negative one mean? Reinforce with them. More positive means it's more likely. Okay. And all of these can be reversed and the value can be reversed. Now, to those of you who are very good chemists, you will know that reversing these and reversing the value does not really make any sense. But in terms of teaching your students, it does. So here we go. Excuse me. Here is something that I do with my students, but if your students are struggling, do not do it because it makes it too complicated. Ask them what could happen. So here are the equilibrias as they would be written as redox. Okay, what could happen? Show them, ask which is more likely to go from left to right. Would zinc pick up electrons better, zinc ions, or would copper ions pick up electrons more likely? What would happen to the metal? Would it go that way or this way? And then show them the numbers. There's zinc at 0.376, and here's copper at positive 34. Remember, more positive is more likely. So that means that copper is more likely to go left to right. And zinc would be, if it could choose, would go from right to left. Okay. So then we can put it together, put the cells together, connect them with a voltmeter, sorry, there, like this. I would talk them through this. Here are the values. What is going to happen? Well, this one is the most likely to go left to right. There are two different ways of calculating what is going to happen. You can use either one of them. In the first one, you draw an axis from negative numbers to positive numbers. The negative number for zinc is down here, the positive for copper up here. We know electrons always go from the negative to the positive, left to right. And we know that the voltage is the difference between them. When this happens, if the electrons are going to go from the zinc to the copper, the zinc must lose electrons. In other words, the zinc must go backwards from zinc to zinc ions and electrons. Those electrons then flow to the copper, and the copper ions pick up the electrons to turn into copper. Okay, the overall voltage is simply the difference between those two numbers, 1.1, and it's positive. It's only negative if you connect the voltmeter the wrong way around. The second way is this. So that's the first one. Negative numbers on the left, positive runs on the right, electrons go left to right. So what happens here? What happens here? That's the system. The second one, we look at these two, and the more positive one goes as it's written. So that one is more positive. That goes in that direction. That forces the other one to go in the opposite direction. If that goes that way, then all I have to do is to add them up. Positive, because that one's going backwards, I've changed its sign. So it's now positive 0.76 and positive 3.4. It comes out with the same answer. It doesn't matter which one you do, it comes out the same. And we now know that zinc turns into zinc ions because it has to produce the electrons, and the copper picks up the electrons, copper ions pick up electrons to produce copper. Now the cell notation has to use that and show that zinc goes to zinc ions and copper ions go to copper. So this is how it is written, like this. Zinc, it goes left to right. Zinc turns into zinc ions. This is the salt bridge. That's copper ions turning into copper. So this makes sense. And the electrons go from here to here. Okay? So that's how the whole thing fits together. That is what we call the cell notation. Okay. Then I give them a number of examples. So here's one. This is silver and lead. If it's silver and lead, then we just give them the numbers. Here's silver, there's lead. And hopefully they will go, okay, I'm either going to do it on a line, negative over here, lead over here, silver over here, or the more positive one goes left to right, the more negative goes backwards, etc. Okay. So I'm not going to do this now. You can see it later. I'm running out of time because we were a little bit late starting back. So I'm going to leave that in. I'll tell you what it is. It's called no hands. It's a very simple idea that you don't allow people to put up their hands in class. You make everybody answer when you point at them or ask them, then use their name to answer them. You have to be aware that sometimes somebody may be very, very anxious. Something bad might have happened at home or whatever. But so you have to be very careful with that. Just going to go back to that last one just in case anybody missed it. So this is how we do it. Here's the example. Have a look at it yourself just before we stop. Here it is. Here's the silver one. Here's the lead one. More positive ones are more likely to go left to right. So I can either draw it on a line. So I can either draw my line and go negative down here. So this is, whoops, sorry. This is 0.13 negative. And that's the lead one. And then up here is the silver one. And this is positive 0.8. The electrons go from left to right. So that means that the lead must produce electrons. So the lead, it must be written in this way to produce electrons, which then go in this direction. And the silver must pick up electrons to use them up. Never change the values. Just because I would need 2 silvers doesn't mean this becomes 1.6. Okay, we don't do that. Either that as a method, which is very simple. Some people like that one, or I go, okay, the silver is the most positive, so it goes in this direction. The lead is less, and that is plus 0.8, and the lead is reversed, so it goes here in this direction. Lead turns into lead ions and electrons, and therefore I change the sign and it becomes positive 0.13, and therefore the total is 0.93. Whichever way I do it, that is the voltage of the whole cell. Now, because I know that lead turns into lead ions and silver ions turn into silver, my cell notation will start with lead, phase change, lead ions, because that's the way it's reading. Here's my salt bridge, and my silver ions turn into, whoops, sorry, what am I doing there? Stupid boy. Ah, come on, come on, come on. Ooh. Phase change, silver. So these always read in this direction, and the electrons will go from the lead, whoops, sorry about my arrow, to the silver ions. Okay. Okay, so no hands, use no hands. Here's another one of those thinking things. If I switch the lights off in a room, will the walls change color? Will they? Think about it. Okay, after lunch, we're going to be doing this. But I think now it's time to stop. So we're going to stop. You will get all of these presentations, all of the examples, all of the worked examples, all of the answers. So you can look at them yourself if you want to. If you have questions, if you could give it to one of the, like Michael or Fatma and so on, and they could send me it over lunch so I could have a look at it. So I can try and answer any questions if you've got questions. It would be good if they were concise questions. If they're examination questions, that's fine. But there's quite a lot to do. I don't want to cut down on answering questions or helping you with problems. But what I'm trying to do is to give you an idea of how you can present this in a simple way to your students. If you look at what we've just done in electrochemistry, we have covered a huge amount of information. You know, to go from redox and oxidizing reducing agents through electrode potentials to voltaic cells, that's a lot of information. This would take you weeks. So I'm just trying to show you a way through it that makes it simple in that I do it, we do some together, and then they do examples. So you're not the person doing all the work all the time. But now it's time to stop so you can go again. And I'll see you later. Okay? Everybody alive? Kasumu, are you alive? Yeah, Kasumu is still alive. Okay, I haven't killed them yet. Good, excellent. Mathari, you've got more than just the top of your heads. This is good. Good, excellent. See you later, guys.